Right, so dynamic nuclear polarization, starting a series of 4 lectures on the subject. Simulation, equipment, and then some applications. But beginning with the simulations. It's a fairly rich topic, and simulation-wise fairly recent. Rather difficult, and we'll be doing perhaps well, the most general version. So I will not assume one electron and one nucleus. I will not make any simplifications, at least at the beginning. So we'll just go through the system in its most general case, and then we can simplify into the various special cases. So in essence, in a DNP instrument, we have a number of nuclear spins, and around them a number of electron spins, which interact through both the dipolar interaction through space and possibly through contact interaction if there happens to be some electron density at the point of the actual nucleus. Now, in liquid state, you know the situation. We went through Redfield theory and dipolar spectroscopy. What would happen there is we would have a cross-relaxation between the electron and the nucleus, and if we invert or perturb the electron, that would propagate to the nuclei. Now, so in liquid state, DNP is just a special case of Redfield theory and the dipolar cross-relaxation that we all know and love. But in a solid state, it is rather different, and so what I will focus on today is specifically solid state DNP. And it is also a situation where much larger enhancements are possible compared certainly to those realistically attainable in liquids. So the most people could ever do in liquids was maybe a factor of 100 on a very, very good day. But in a solid, it turns out that in favorable circumstances, it is possible to essentially polarize the nuclei 100%. At least people have got into the 80 to 90% region without various impossible difficulties that would be encountered in liquid states. Okay, so we have a bunch of electrons, possibly interacting electrons, and that's important for things like cross effect. And we have a number of nuclei in the system. And so our Hamiltonian is going to contain various terms. Now, the obvious thing is the Zeeman interaction, so we will have H Zeeman containing the interaction of both the nuclei and the electrons with the magnetic field. Then there would be interactions between nuclei, so nucleus to nucleus, which in this case we certainly cannot ignore, because the polarization accumulation itself might be relatively independent of this term, but then the diffusion of the magnetization through the spin system definitely involves this part, so we need to put it in any good simulation. The critical part is the electron-nuclear Hamiltonian, so contact interactions, hyperfine interactions, and the special case of a hyperfine interaction called the dipolar interaction. And then, inevitably, if we have multiple electrons, we would have the inter-electron couplings, so they would interact through dipolar interactions, through space. And if they're sufficiently close together, there might appear exchange interaction, which is a fancy term given to just an isotropic coupling term between the two electrons. And of course, we will have relaxation in there, but I'm not putting it in at this stage because this is just a Hamiltonian. What I will put is the last necessary ingredient for DNP to happen is the microwave irradiation. So that is the basic setup. We've got all of this, and all of this is fairly complicated. And you can see how you start needing automated software that would actually construct this Hamiltonian for you.
So this
based on the...
Sorry, it's HNN, nucleus. This basically includes all this, like dipolar interaction, quadrupolar.
J couplings, dipolar, quadrupolar, absolutely everything, yes. J couplings, I think one could realistically at least try to ignore. But the problem with DNP is, in a typical experiment in a solid state DNP, it takes multiple seconds for the polarization to accumulate. And on that time scale, even a J coupling is significant. And so J commutes with the Zeeman order So it might not be that consequential, but in principle it has to be there because it does have the time to manifest in those experiments. Right, so let's just go through each term one by one and look at what we've got inside them. So HZ, Zeeman Hamiltonian, would have been simple if we had it in a liquid, but we have it in a solid. So it is anisotropic, it is orientation dependent, and so we must put in the full buck. So we will sum over the electrons, so sum over K, B0 vector, then the Zeeman tensor of the kth electron in the system, and then the Zeeman operator for the kth electron. Yes, so Ex, Ey, Ez, the spin operator. The same for the nuclei, so again this second sum would be running over nuclei, so we would have B0, then A, N for K's nucleus, and then N, K spin operators. So we'll denote them E, and we will denote them N for the electrons and the nuclei respectively. Now, it is important to realize that it is next to impossible to co-crystallize a radical into a solid matrix, and so what we will typically be dealing with is a glass, which means full orientational averaging, which means a proper honest simulation would need to be powder averaged with respect to orientations, and therefore this all implicitly also includes rotation operators decided for that powder averaging. So you can see how the problem complexity grows in front of us. Right, so H nuclear would contain our J couplings, for which I will just assume the angular frequency units, so I don't have to worry about those pi's and 2 pi's. So J nuclear between nucleus J and nucleus K, and then just the nuclear spin operators, so and J scalar product and K. So that's the J coupling minus the usual dipolar interaction between the nuclei. So mu naught over 4 pi gamma n of the J's nucleus, gamma n of the K's nucleus over this R K to the fifths, and then the usual dipolar brackets that goes as R squared, and so the asymptotic behavior is 1 over R cubed. So this is orientation independent, whereas this rotates as a second rank tensor in the way that we discussed in the rotation lecture. So both this and this needs to be included. Now, what we'll use later when we deal with rotating frame transformation is actually an irreducible spherical tensor form of this, which hides all the fundamental constants and all the Hairy expressions under just blanket coefficients and the spherical tensor expressions. So again, we do have to sum over J and K, so over pairs of the nuclei, where J is just smaller than K to avoid double counting in there. But then at that point, it's a fairly anonymized sum over the coefficients. So we would have it D nuclear, then J, K, L, M, and then T, L, M operator between the nucleus J and the nucleus K. So that's just a shorthand here where all the numerical factors have been absorbed into these coefficients, and the expressions for irreducible spherical tensors you have all seen in the previous lectures. They just contain all these various operators. But it's useful to express it in this form because these things are a bit easier to rotate than these things, and it's certainly a lot less messy when you're rotating them. Now, obviously, the only ranks which are present in L are 0 and 2. It's 0 for the J couplings because they're fully isotropic, and 2 for the dipolar coupling because it rotates as a second rank spherical harmonic. So that's our expression for the internuclear Hamiltonian. Now for the electron nuclear, H, E, N, we just have the hyperfine coupling, so we will have to sum again over J and K, where J runs over the electrons and K runs over the nuclei. And usually everything interacts with everything because electron-nuclear dipolar interaction is very long range. And so we would have EJ, vector operator, times AEN, so electron-nuclear interaction, then JK, and then NK interacting with the K's nucleus. And just as we did for the internuclear coupling, we'll also have a spherical tensor expansion for that. So it will be JK and then a sum over LKM of basically an identical expression, except the coefficients will then refer to the electron-nuclear interactions. And the operators, the first spin would be the electron and the second spin would be the nucleus. So D electron-nuclear, then J, K, M, and the TLM spherical tensor operator between a spin J and a spin K. Again, it will become necessary when we start doing the rotating wave transformations. Now, the inter-electron Hamiltonian, interestingly, looks basically identical to this, except for the ends which are replaced by E's. The isotropic coupling between electrons is known as the exchange interaction. It, as I did explain, I think almost a year ago now, to this audience, the consequence of the non-classical part of the Coulomb interaction, the anti-symmetry principle, it just emerges out of it. And electrons do have the same dipolar interaction as the nuclei do, although because electrons needn't be point particles, in fact in most cases they cannot be considered point particles, you might have to take an integral over density distributions of those electrons. But in practice, I've yet to see a paper that goes to that sort of length. People always assume point dipolar interactions between electrons, even if they include them at all, which is also something that sometimes is made as a simplifying assumption. Right, so these are the inter-electron couplings, and finally what we need to include is a microwave term. And that's just a cosine modulated wave that is instrumentally a rather difficult thing to get, particularly in very high powers, but mathematically is not particularly difficult. So H microwave is going to be just a cosine modulated wave. So cosine omega microwave T. Note that omega is frequency here, not the power. The power I will call A. And there's an interesting twist here. You see, electrons do not necessarily have the same G factor. Or they might have the same G tensor, but they might be in different orientations. And so the response of each electron to the B1 field that comes into this microwave might be different. Yeah, it might be converted into frequency with a different coefficient because the orientation of that electron is different. And so, strictly speaking, even though in the microwave term all electrons will see the same frequency of the microwave, they might see slightly different amplitudes of it, and so the amplitude has to be taken into a sum with an electron-dependent coefficient. And so what we are going to have in there is A, the amplitude of the microwave, which would be specific to the case electron, and then multiplied by EX. And without loss of generality, we'll just assume that our microwave radiation is applied along the x-axis. Could be Y, but it's ultimately just the way you choose it. And it is usually the case in such experiments that the field is applied perpendicularly to the direction of the magnetic field, or rather, to put it more precisely, the parallel component doesn't matter because we are doing a rotating frame approximation and then averaging with respect to various carrier frequencies of the electrons in the magnet. Okay, so we'll do a little bit of transformation here. This X operator doesn't play particularly well with rotating frame transformations, and so we'll just express it in terms of the plus operator and the minus operator. Similarly, the cosine is best just expanded into a pair of complex exponentials.
Sorry, why do you have cosine in the first place?
Cosine.
Shouldn't it be exponential, because magnetic field it's electromagnetic field and it's usually...
We don't see the electric component in there because our spins are magnetic dipoles.
Okay.
Generally, electric field is there, but it's basically just causes heating of the sample. It does not affect the spin. And then, okay, generally speaking, we can have a circularly polarized magnetic field, but instrumentally it's very difficult to achieve. So what people essentially do is at the entrance, at the exit of the waveguide, that brings in the microwaves, there's your sample. And if you look at the component of the magnetic field, it just oscillates like that. So it's a cosine oscillation rather than a complex exponential. In practical instrument, I think it's next to impossible to tell how exactly your waveguide couples to your cavity. People do these complicated calculations, but then in an actual sample which is polycrystalline and heterogeneous, goodness knows. So this is one of the simplifying assumptions, I guess, that we have in there, which seems to match the experiment. That having been said, I've yet to see a theoretical simulation of DNP actually being compared to the experiment, because of all these various complications and of the heterogeneity in the system. It's very difficult to compare. Because imagine you have many nuclei around many electrons. You don't just need to average over all possible orientations of the sample, but you have to average over all possible distance distributions in there, because the sample is not of a regular structure. So it has to be averaged over orientations, but also averaged over molecular disorder. And again, this is work in progress. I know people are working on it, but I've yet to see it actually done. And so all of this rigor is good if you have a very precisely geometrically defined system. It is rather less good if the system is ill-defined to start with. And so, this proceeds on the assumption that the system is well characterized. If it's not, it has to be done multiple times for the various distributions you have. Okay, so let's just expand that. So it will be E minus I omega microwave T plus E plus I omega microwave T over, well, initially 2, but I'll do the same to this, so actually 4. And then a sum over K microwave on the case electron, and then E plus E minus K. So that will be the operator that we are actually going to use in there. Right, so we are all set. And so what we now need to do is to proceed to a simulation with this Hamiltonian here. We immediately hit a snag with that simulation. DNP is a time domain phenomenon. It accumulates, we need to get the shape of that curve, we need to find out how long it takes. But we do know experimentally that it takes multiple seconds, in rare cases multiple hours. What we do have here, however, is almost a terahertz. In a high field, the electron Zeeman frequency. So if we were to propagate it honestly under the full Hamiltonian that we have, that would either take an impossibly long time if we propagate it with an appropriate time step, or would lead to huge numerical inaccuracies, because we do actually need to sample everything, including this time-dependent radio frequency field, microwave field. And so, both because the dynamics of the system that's intrinsically in there is very fast, and because we do have an oscillatory time-dependent term which basically hits the system at a similar frequency, to properly sample that waveform, we would need to take sub-nanosecond steps, and that means 1 billion steps per second, and if you are polarizing for a few seconds, that's the end of the calculation. The computer is not fast enough to properly do it. So the QR is the same as what we do in the rest of the magnetic resonance. The cure is the rotating frame transformation. But what we will do here is do a bit of prioritization. If we simply had large eigenvalues here, that's not a problem. I mean, we can do it with scaling and squaring, we can do the long-term propagator, it's gonna be fine. But if we have fast time dynamics here, then we really have to sample that dynamics. And so the priority is to get rid of the microwave here and to transform the problem into a form which involves a time-independent Hamiltonian. Because as soon as it's time-independent, things get considerably simpler on the simulation side. So what we'll do next is to actually carry a rotating frame transformation with respect to a microwave frequency. So our H0 in the rotating frame expression is going to be omega microwave times the sum over the electron operators. So with that in place, we will move into the frame that rotates with at least one of these two frequencies. The other one we will conveniently ignore, citing the average Hamiltonian theory, because it's so far off resonance. But let's just run this rotating frame transformation and see what happens to the Hamiltonian. Let me just wipe the board. So all of this is implemented into Spinach as a black box. There are examples, so you just download it, open one of the examples, modify your own to match your own system, and press enter. It is going to run, but I guess this is an illustration into what went into it when we were programming. Right, so when we do a rotating frame transformation, this Hamiltonian is subtracted from the Hamiltonian that we are transforming. And the various things involved acquire a time dependence. So let us go through each of the terms in here, take a look at what they do and how they transform under this Hamiltonian, and then decide what we can ignore and what we cannot ignore in the resulting rotating frame. So the Zeeman Hamiltonian, Hz prime, well, this is a Zeeman type rotating frame transformation. So H0 will just be subtracted from the previous Zeeman Hamiltonian that we had. And so what we will have is a sum over k, omega e, k, the frequencies that were there before the rotating frame transformation. Then this gets subtracted, so minus omega microwave on Ez. Okay, if we had some E pluses and E minuses, they can be ignored in the rotating frame. So we just have the usual Zeeman interaction at a particular orientation, perhaps. Omega E might be orientation dependent. Plus we have the same nuclear term. It just remains unchanged because nuclear operators commute with the electron operators, and so that rotating frame transformation has no effect on the nuclear part. Let's take a look at the microwave operator. So what happens to H and W? What would happen is an exponential of this would be applied to E plus and E minus. And I'll remind you that Lz, L plus commutator is equal to L plus. And therefore, as a consequence of this, you can prove it yourself, E I omega Lz acting on L plus is equal to E I, so it should be T, E I omega T L plus. So, under the action of a rotating frame transformation, the plus terms acquire positive frequencies and the minus term will acquire the corresponding negative frequencies because of this commutator here. So if we apply that to the microwave, what we are going to have is, I've just rewritten the previous Hamiltonian in your equation 10, but I've added the frequencies to the E plus and the E minus in the round brackets. So we've got E minus I omega microwave T plus E I omega microwave T over 4. That was the cosine modulation term. It's a scalar modulation, so of course it remains unchanged. Then a sum over our electrons. A microwave, the amplitude that's held by the case electron. But then we replace E plus with E plus times a frequency, and E minus with E minus times a frequency. And the frequency is here. So what we will have is E I omega microwave T E plus K plus E minus I omega microwave T E minus K. Okay, and now we just need to open the brackets and decide which frequencies we are interested in and which frequencies we are not. So 1/4 a sum over K A microwave case electron, and then the brackets. Now this will cancel with this, and so we have a static term which is E plus K. Then this will not cancel with this, it will just double, so we do have E minus I times 2 omega microwave T acting on E minus. Then another term with double the frequency, but it will be double the frequency of the opposite sign. So I 2 omega microwave T E plus K, and then plus E minus. That should be K. So in the spirit of the average Hamiltonian theory, and I am skipping a couple of stages of mathematics here for the sake of time. This goes back to, I think, Copernicus, no less. We can say that if we do have a static part and a very rapidly oscillating part in the Hamiltonian, then the rapidly oscillating part can, to a good approximation, be ignored. But you can probably ask, well, why didn't you ignore it earlier? So a correct argument to this effect would need to take the average Hamiltonian to second order and demonstrate that these terms do survive and those terms disappear, and then you'd have the electron frequency in the denominator in there, which makes the term very small. So skipping all of that, see the average Hamiltonian theory lecture, I am destroying these terms. And so what we're left with is now time independent. 1/4 a sum over K, a microwave case electron, E plus K plus E minus K. So in our rotating frame, that is rotating with respect to the microwave frequency, the microwave term becomes time independent. As we found, the Zeeman term is also time independent, so what remains for us to do is to take a look at all the other terms and see what happens to them. Now, your handout contains a bit of a quantitative argument to the effect, but it's quite a lot of writing which is not particularly instructive, so I'll just walk you qualitatively through what would happen under such a transformation. So we established that the Zeeman interaction doesn't change particularly much. It's the frequency that is slightly different. I mean, this becomes something of the order of the nuclear frequency. Microwave is usually on either the double quantum or the zero quantum transition in there. Now, for the electron nuclear term, what would happen is we would move into the rotating frame with respect to the electron, but not with respect to the nucleus, because this stuff commutes with nuclei. So the only things that would remain stationary under such a transformation are operators of that type, Ez and whatever. So if it's E plus, it will acquire frequency. If it's E minus, it will acquire frequency. If it's Ez, it would not. But it doesn't really matter which state the nucleus is on. That operator commutes with it. So the only terms that would survive in the electron nuclear part are the so-called secular and pseudo-secular terms, and the weak terms as well. So the weak ones are the EZn Z, and the pseudo-secular ones are the EZn plus and EZn minus. Everything else will be obliterated by the rotating brane. As for the electrons here, it's the same situation as we had with J coupling and dipolar coupling in the rotating brane transformation lecture. So the stuff that would survive here are operators like this, E1Z, E2Z, which simply commute with this transformation to start with, but there will also be terms like E plus, E minus, 1 and 2, where this rotates with a positive frequency, this rotates with a negative frequency, and the frequencies just cancel one another in the end. And so it also remains stationary under the transformation. Everything else will be removed. And so that's it. We do now have at least an understanding of what happens to each of these terms. If you are doing practical calculations, it will take you a very considerable time to implement it all and incorporate it all and put all the various assumptions in and make sure your Hamiltonians are generated correctly with the correct kind of terms. Hence the number of simplifications that you would typically encounter in the literature. Of course, nobody wants to do it by hand. And so they simplify the system to the barest bones that they can get away with. If you are using an automated software package, then of course there is no need to do so. And all of these terms are there in practice. Okay, so the thing that remains now is, to run the actual simulation. And after everything that's been said and done here, we do have our time-independent Liouvillean. And under that time-independent Liouvillean, we can run the simulation. Now, there are two practical snags in there. One is, even though we have actually knocked our biggest frequency from the order of gigahertz into the order of megahertz, it's still an order of megahertz, which means a few million steps per second. That's less hard than the previous problem, and it's certainly not time dependent anymore, so it's a lot simpler, but it's still a pain. In particular, it's a pain to generate the propagators, because, we can scale them, but then we'll have to square them at least 20 times to get them back into the second scale propagation from microsecond scale propagation. And that's okay, but it puts a bit of a strain on the numerical accuracy. But let's just put it that way, it's doable. So our final Liouvillean that we will be propagating under, therefore, is L double hat, so that's the stuff that goes into the matrix potential again. So is Hz prime, so rotating frame Zeeman, plus H internuclear prime, rotating frame internuclear, plus H electron nuclear, plus H interelectron, plus H microwave, plus, importantly, relaxation superoperators. So that should be commutation superoperators, plus IR. And what is particularly important is the relaxation superoperator should be thermalized. That is, it should not be driving your system to the zero state, as vanilla Redfield superoperator would. You need to take care to actually make sure that this thing is driving you to the correct thermal equilibrium. There are multiple ways of doing it. This is a relaxation theory lecture, but it is essential that this is thermalized, otherwise it simply wouldn't work. And well, if we require time dynamics under this Liouville, then the magnetization of the nth nucleus, so let's say nth nucleus as a function of time, would just be the projection onto the corresponding operator of the same nucleus of a matrix exponential. The Liouville is now time independent, so we can do it. And then the equilibrium density matrix. Because we usually start the thermal equilibrium into DNP experiments because it requires some time and sometimes considerable effort to actually get the electron to equilibrate, to acquire the huge polarization, which we then transfer to the nuclei by blasting it with microwave. And well, this is done in the usual way. We discussed it in the previous lectures. We can compute the matrix representation of this exponential. We push the system forward. We watch the nuclei being polarized. Now, it is rather inconvenient in practice if you only want the equilibrium polarization. Because the equilibrium polarization corresponds to t equal to infinity. The practical approximation to infinity is a couple of 100 seconds. But it would still be a very long propagation, and you've got to make sure that everything's equilibrated and so on. So if you need a time trace of what goes on, that's the way to go. But if you need a steady state situation, then there is a neat trick which solves for the steady state straight away. Now, for a differential equation, what's the definition of a steady state?
No space.
Hmm?
No space.
So yeah, basically the time derivative is zero. So it no longer evolves. So in our Liouville von Neumann's equation, so d rho of t by dt minus I h superoperator plus r superoperator acting. I would rather actually write it differently just to expose the thermal equilibrium specifically. So let's do it this way. H acting on rho of t plus relaxation superoperator that's pushing the system from its current state into the thermal equilibrium. Like that. And so at time infinity, this is 0. And this we can actually solve for rho infinity. So minus I h rho infinity plus r rho infinity minus r rho equilibrium equals 0. So I'll just take rho equilibrium to the right hand side, and I'll take rho infinity out of the bracket in there, so it will be minus I h plus r rho infinity equals r rho equilibrium, and we are just one step away in here. We just need to take the inverse of this and apply it here. So rho infinity is minus I h plus r inverse r rho equilibrium. In practice, one does not need to compute this matrix inverse because what is acting on is a vector, and an inverse times a vector is a backslash operation in MATLAB. Dima might ask a reasonable question as to whether this inverse always exists, but because rho is always negative, definite, and never degenerate, and h is Hermitian, it can be shown that this inverse does in fact exist in all circumstances. And so then the projection of this onto the nuclear magnetization operator will give you the equilibrium DNP in your system at the cost of basically one cubic matrix operation, or even cheaper if it's a matrix vector operation, rather than multiple steps of this propagation here, and various intermediate results if you need to do it for multiple different frequencies in the Hamiltonian. The intermediate Coulomb spaces can be reused, and so it can be a fairly fast calculation if it is set up properly.
So the relaxation doesn't actually drive us to equilibrium state, but we will, on infinity, we will come to some other state, which is rho of infinity, which is not equal to equilibrium.
Well, this is a thermalized one, so this is the one that drives you to equilibrium. This, importantly, is not a thermalized one, so this is the one that drives you to zero. So it will drive this difference to zero, and therefore it will drive rho to rho equilibrium. Yeah, there's a difference between rho th, RTH and just R.
Yeah, but in fact we don't, on infinity limit, we don't come to equilibrium,
We
come
don't.
to our other state.
We don't. That's because there is microwave irradiation here. Yeah, we blast the system with microwaves, so its steady state will be different from its thermal equilibrium.
But just if you consider energies, for example, you push your system with some microwave, it costs you some energy. And how can we be sure that the system actually converges to something rather than go to infinite temperature or something like that and destroy it?
There's always dissipation, and there's always the heat bath. So typically a spinning sample will just dump the heat into the spinner, and the spinner will dump it into the spinning gas. And so, yes, an isolated system will definitely go to an infinite temperature. And you are right in that we are actually calculating here the thermal equilibrium of the system with microwaves on, which is different from the thermal equilibrium of the system with microwaves off, which is where R has been.
Yeah, just mathematically, I'm wondering why this process converges to constant rather than converge to
some
periodic
orbit or a loop.
Well, yeah.
Because this is physical reality. And there's plenty of friction in the system,
Mm-hmm.
and so all orbits do converge under the dynamics with friction. So yes, if we do have extremely slow relaxation, people did show that in solid state you do populate those periodic orbits, the so-called quasi-equilibria. They are known to exist, but to my knowledge none have been discovered in DNP systems. Probably because electron relaxation is extremely fast, and the powers of the microwaves that we apply are, at least for now, reasonably low. So we're talking watts to kilovolts at the moment, because otherwise the sample simply boils. Right, so that is, or rather that was, an outline of the most general possible case. You would notice that we placed no restrictions whatsoever on the system, apart from it being at high field. And that requirement ensured that we could make the Liouville time independent by going to the rotating frame transformation. We placed no constraints on the frequency of the microwaves. They could be anywhere, again, so long as the rotating frame transformation applies. In practice, that means between hundreds of megahertz and hundreds of gigahertz, anywhere. We placed no restrictions whatsoever on the interactions, on the relationship between various parameters in there, on the presence or absence or anything. There could be inter-electron couplings, there could be internuclear couplings, anything at all. So the spinach module called DNP exact implements this case. The downside, however, is in the time domain is a bit of a long propagation under a bit of a high frequency. And in the frequency domain, it's still an inverse of something with pretty large eigenvalue distributions. And so it works, but we can ask the question of whether in a practical reality of a given DNP experiment, there might be some further simplification of this. And so we come to the second stage of the lecture. I'll go through something that is called solid effect DNP. And you must have come across it in the various lectures and conference talks and papers by now, particularly those of you who do cryo NMR spectroscopy. So the particular twist that solid effect DNP makes is to fix the frequency of these microwaves. It is agreed as a part of the experimental setup that the frequency here, omega microwave, shall be equal to omega electron plus or minus omega nucleus. If it's plus, then we are irradiating a double quantum transition. If it's a minus, then we are irradiating a zero quantum transition. Up to the sign of the resulting magnetization, the result is basically the same, as we'll see at the end of the lecture. And so that's one thing. The other thing is we assume, so let's say that's assumption number 2. Assumption number 1 is that we have a single electron.
So the second one, omega microwave is equal to electron. That was not the case for liquid state, DNP?
No, in liquid state you do have to blast the actual electron, to my knowledge, to do the Oberhauser DNP. So it's a bit of a terminological difference. I guess you could try doing a solid effect DNP in a liquid.
By liquid DNP you are not meaning like polarizing solid state and then make dissolve. It's not. Is it liquid DNP?
No, liquid I mean when you are actually blasting a solution with microwave.
Microwave.
So Oberhauser DNP, I think it's
So the
known.
the dissolution DNP is basically solid state.
Is basically solid effect followed by dissolution. I must admit, when people first started talking about this dissolution DNP, you know, shooting superheated methanol across the lab, I thought that was never going to catch on, but it did. So yes, I was proven wrong. Okay, so we assume single electron, which basically means we don't need to worry about this. We have a very specific form of our microwaves now with a particular frequency.
Sorry, what do you mean by single electron? The system
Just
has
one electron.
You have
One unpaired electron.
one
I'm
unpaired
sorry.
electron. Okay.
Yes, we tend to forget, of course,
Yeah. Okay.
anything that's non-magnetic.
Right, but in our previous derivations we considered different orientations and so on. Is it still the case for single electron?
Yeah, it may have an anisotropic G-tensor, and yes, it will have to be done.
Okay.
In fact, most G-tensors, unless it's something really regular, most G-tensors will be anisotropic. And God forbid if it's some heavy metal like gadolinium, and then it would be anisotropic to the tune of, 20% or so, and it really starts to matter in that case. Right, so that's our first assumption, that's our second assumption. There was a third assumption saying, oh yes, we will further assume that all nuclei have the same Zeeman frequency. So all nuclei have the same omega n. In general case, this is manifestly untrue. We would have protons in the system and we would have carbons in the system, and even carbons would differ a little bit, and they would differ by a couple of 100 hertz, maybe a couple of 1,000 hertz, and on the scale of the solid effect DNP it really does matter that dynamics has time to occur, but this is one of the simplifying assumptions in the, at least the neat theory of solid effect DNP. If we were to lift all of these assumptions, we would just have to do what I've just described. There's a full wax system. But in order to achieve some simplification, which we can basically get away with, it turns out, without too much accuracy loss, we shall make these three extra assumptions. So our Zeeman Hamiltonian in this case, Hz, simplifies very considerably. It becomes just omega e Ez, so just one term because we only have a single unpaired electron in the system at this point. And then the same frequency omega n for all the nuclei, and then we have a sum over k and zk. And what we will now do is different from what we did in the previous description. Instead of doing a rotating frame transformation with respect to the microwave frequency, we will do a rotating frame transformation with respect to this entire Hamiltonian. And the result would be that it would disappear altogether from the Hamiltonian, so it will be subtracted. But we will be left with some time dynamics in the other parts of the Hamiltonian that we have. So just as we did for the previous case, let's just go through all the parts of our Hamiltonian and see what happens to them under that transformation. Right, so let's just go in order. So Hz prime just goes because we are doing a rotating frame transformation with respect to it. So it gets subtracted out. H internuclear is invariant under the electron operators, but not invariant under the Zeeman nuclear operators. So it will acquire some frequencies under the bonnet. So what we will have is Hn prime would be, I'll just use that spherical tensor expansion. That was the reason why I wrote it out to start with. So a sum over j less than k, a sum from m minus 2 to 2. The isotropic j couplings are invariant under the rotating frame transformation there. So d, j, k, m, and then a frequency e, I, m, omega n t applied to t2 m j k. And the reason this frequency appears is the following commutation relation: Lz commuting with t Lm is m t Lm. And so if we are applying a rotating frame transformation under the commutation operator with Lz, a frequency will pop out multiplied by this number m. And so that is that frequency that comes out, and the spinning rate of the rotating frame is equal to the amplitude of the angle by which we are spinning. So omega mt is that angle. So we do have frequencies here, and so the only term that's properly frequency independent here is the secular one with t0, but it turns out that we cannot just simply go and ignore them. That would be approximation that's too rough, and so we will have to go and do the average Hamiltonian theory in the end when we are done with writing all of these things out. Now there is a similar transformation in your handout that's applied to the microwave term. It's a lot of writing in there, so I'll just skip the derivation and I will only write the result on the board and explain what that means. So after we ignore the very high frequencies, which we clearly can ignore in there, what is left is the following: a microwave over 4, and then e I delta times t, e plus e minus I delta times t multiplied by e minus. And those are the electron operators. So where delta is the difference between the frequency of the electron and the frequency of the microwave, and by assumption in here that is chosen to be the frequency of the nucleus or minus the frequency of the nucleus. So plus minus omega n. So we are irradiating either a zero quantum transition or a double quantum transition. Now in the electron nuclear term here, what would happen is the non-secular parts of the electron operators, E plus and E minus, oscillate so quickly they really can be ignored. So the only stuff that survives is the stuff that contains Z. Again, a quantitative argument can be made with average Hamiltonian theory, but that is skipped for lack of time. But with respect to the nuclei, we still would have to keep absolutely everything, because yes, those frequencies are of the order of megahertz, but there are other things present in the system of the order of megahertz, and so the various interactions between those megahertzes cannot be ignored, and so we just keep everything on the nucleus, so weak and pseudo-secular terms of the electron nuclear coupling. Right, so after all of that has been done, there's a monstrous set of equations in your handout, equations 19, which contain explicitly, not in a spherical tensor form, but written out, all the terms that carry either no frequency, so that's H0, or a single unitary frequency, so they oscillate at omega n, that's H plus and H minus, or in some cases they can oscillate at twice omega n, and that's H double plus and H double minus. And so ultimately what we are left with is a Hamiltonian H in our rotating frame, which has 5 terms in it. It has E minus 2I omega m t H minus minus. So the form of it is given in equation 19 for you. Then E minus I omega m t H minus plus H naught plus E I omega m t H plus E2I omega m t H plus. So a fairly complicated time-dependent situation in which, however, this time dependence is on the exponentials rather than inside the Hamiltonian. So each individual Hamiltonian here is time independent, and the frequencies that go into it are relatively small. So they are electron nuclear couplings of various kinds, so maybe units of kilohertz to units of megahertz, so much smaller than the nuclear Zeeman frequency. And so even though we put these oscillatory terms in front, in terms of the energies that go into the Hamiltonians here, we have really slowed the system down to a very considerable extent. So we now have a periodic Hamiltonian, and we require an average Hamiltonian, the effect of which would approximate the effect of this Hamiltonian, but which would be constant. And that, of course, to all of you, because you've done a lot of solid state and mass spectroscopy in your life, is closely familiar. That's the average Hamiltonian theory. And I did not give you the actual answers in the handout, only because they're really, really huge. Again, symbolic processing software is your best friend here. We just use Mathematica for analytical processing. Spinach has an average Hamiltonian module as well. But I'll just remind you what average Hamiltonian theory was all about to start with. Now, if we have a propagator under a time-dependent Hamiltonian, so P, it would be a time-ordered exponential of minus I integral from 0 to time t of h of t dt. And what a time-ordered exponential was, I explained at the beginning of the course. It's not as simple as taking the integral and then the exponential. It's much more complicated. In the most general case, well nigh incomputable. So that's the propagator of time t. And in the most general possible case, an average Hamiltonian, so average, is defined as 1 over t matrix logarithm of p of t. So it is such a Hamiltonian as would give the same propagator as pt when you propagate under it for a time that's precisely equal to t. So basically the effective Hamiltonian after the evolution period. It does not always exist. Or rather, more specifically, always exists in the unitary case, but not necessarily exists in the dissipative cases, because the exponential map on a semigroup is not necessarily invertible. But after you have done about 10 pages of really complicated algebra, and again see the specific lectures on the average Hamiltonian series, what you discover is that to a first approximation, the average Hamiltonian is equal to omega n. So I just used the notation from our previous derivations over 2 pi, an integral over a single period of the oscillation, so 2 pi over omega n h of t dt, and that's basically a simple average, yes, over the period, and in that case that would basically be equal to h0. And everything else would disappear. I'm not putting it here with relaxation, stuff gets a lot more complicated. Then the second approximation, where the effect of the time-dependent term is included to some extent, involves a commutator, so minus I over 2, omega n over 2 pi, integral 0 to the length of the period, dt2, another integral from 0 to t2, and then dt1, and then a commutator of h hat of t2 with h hat of t1. Now you can see this rapidly gets complicated. Where we had just 5 terms in our h of t, we would have 25 terms in the resulting commutator. But importantly, some positive frequencies would cancel with some negative frequencies in this commutator. There will be some time-independent terms as a result, which would survive the period integration. And so this h1 is actually non-zero. And then there's an h2, which is in your handout, so just 2 nested commutators, and then this h3 and so on. And in the limit of infinity, it does converge to this most general expression for the average Hamiltonian. Again, this is something that a human should never do by hand. Use symbolic processing software. But after we do that, in the case of DNP, see Walter Kuchenberger's recent papers. They use a slightly different flavor of the average Hamiltonian series, but the principle remains the same. We do get a time-independent Hamiltonian with really quite slow evolution, so it can be propagated very efficiently. That describes the DNP effect. And that's it really. The rest is computation. And I think you can just about guess from this lecture that there's a fair number of technicalities here, just buried under all this formalism and a lot of algebra as well. Okay, that's it for today. Questions?
What's the difference between electron and nuclei frequencies? Is it one is megahertz, another is gigahertz?
So omega E is of the order of gigahertz. Omega N is of, well, let's put it that way, omega E in a typical modern magnet is about 400 gigahertz. So top-notch recent development EPR spectrometer. In the same magnet, the omega N would be of the order of 600 megahertz.
That means that your microwave should be accurate to 3 digits, which is possible.
It is, yes.
I see.
There are very high quality sources that do provide that level of control.
Okay.
In principle, you can just blast it on the electron transition, and there will be still some DNP, wouldn't be very efficient. So. Because you see the DNP effect from irradiating on the plus side is opposite to the DNP effect that comes from irradiating on the minus side. So if you're not accurate and you blast both, then the effect is zero.
Okay, and how many of these terms do you need to obtain a relatively good average
Up to H2. So we tested it numerically. The first part of the lecture described the exact formalism. So I tested it against the exact answer, and you basically need it up to the second order. That's fine. The reason is, once you've done this integration, every time you integrate, 1 over the frequency pops out. And so H1 is of the order of 1 over omega n. but H2 is of the order of 1 omega n squared, and so on. And when omega n is 600 megahertz, it converges really rapidly.
Okay, and why do you remove relaxation from this equation?
Because the theory itself, in the derivation of it, at a couple of stages requires the exponential map to be mutually unique. So that there should be a tangent space transformation on that group.
Okay.
And if it's a semi-group under relaxation, then there's no tangent space, there's a tangent cone, and that
Okay.
transformation is not unique. And so very strictly speaking, you could sort of put relaxation into there, and it might work, but it's not a steady ground.
Okay, but if you just throw away the relaxation, you change your Hamiltonian, you solve another problem.
What we usually do is we do the average Hamiltonian, and then we add the relaxation to it.
Got it.
It doesn't play well with average Hamiltonians here. Or rather, it works, okay, if you put it into there. It's just you have to be careful. Okay.